Transformers are essential components in electrical power systems, serving to step up or step down voltage levels to efficiently transmit and distribute electricity. They operate on the principle of electromagnetic induction, where a changing magnetic field produced by one coil induces a voltage in another coil. Understanding transformer basics is crucial for anyone working with electrical systems. A transformer consists of two or more coils of wire, electrically isolated but magnetically linked, wound around a common ferromagnetic core. The primary coil is connected to the source voltage, and the secondary coil is connected to the load. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. If the secondary coil has more turns than the primary coil, the transformer steps up the voltage. If it has fewer turns, it steps down the voltage. The voltage ratio is directly proportional to the turns ratio. For example, if a transformer has a primary voltage of 120 volts and a turns ratio of 2:1, the secondary voltage will be 60 volts. Conversely, if the turns ratio is 1:2, the secondary voltage will be 240 volts. Transformer calculations often involve determining voltage, current, and impedance relationships. The basic transformer equation is voltage primary divided by voltage secondary equals turns primary divided by turns secondary. Similarly, current primary times voltage primary equals current secondary times voltage secondary, assuming an ideal transformer with no losses. In practical transformers, losses occur due to factors such as core magnetization, winding resistance, and leakage flux. These losses reduce the efficiency of the transformer, which is defined as output power divided by input power. Transformer impedance is also an important consideration, especially when analyzing short-circuit conditions. The impedance of a transformer limits the fault current that can flow during a short circuit, protecting the equipment from damage. Transformer impedance is typically expressed as a percentage of the transformer's rated voltage. For example, a transformer with an impedance of 5% will limit the fault current to 20 times the rated current. Three-phase transformers are commonly used in power distribution systems to transform three-phase voltages. They can be configured in various ways, such as delta-delta, delta-Y, Y-delta, and Y-Y. The choice of configuration depends on the specific application and the desired voltage and current characteristics. The delta connection provides a stable voltage supply, while the Y connection provides a neutral point for grounding. When working with three-phase transformers, it's essential to understand the phase relationships between voltages and currents. In a balanced three-phase system, the voltages are 120 degrees apart. The line voltage is related to the phase voltage by a factor of the square root of 3, which is approximately 1.73. This constant is frequently used in three-phase transformer calculations. For instance, if the phase voltage is 120 volts, the line voltage is 120 volts times 1.73, which equals approximately 208 volts. Similarly, if the line voltage is 480 volts, the phase voltage in a Y connection is 480 volts divided by 1.73, which equals approximately 277 volts. Transformer applications are widespread, ranging from small electronic devices to large power grids. They are used in power substations to step down high voltage transmission voltages to lower distribution voltages. They are also used in industrial facilities to provide voltage levels suitable for various equipment. Furthermore, transformers are used in residential areas to step down distribution voltages to the standard 120 volts and 240 volts used in homes. When selecting a transformer for a specific application, it's important to consider several factors, including voltage rating, power rating, impedance, and efficiency. The voltage rating should match the voltage levels of the source and load. The power rating should be sufficient to handle the load demand. The impedance should be chosen to limit fault currents to acceptable levels. The efficiency should be as high as possible to minimize losses. Transformer maintenance is essential to ensure reliable operation and long lifespan. Regular inspections should be performed to check for signs of damage or deterioration. The transformer oil should be tested periodically to ensure that it is free of contaminants and has adequate dielectric strength. The bushings should be cleaned and inspected for cracks or other defects. The cooling system should be checked to ensure that it is functioning properly. Transformer protection is also an important consideration. Overcurrent protection devices such as fuses and circuit breakers should be installed to protect the transformer from overload and short-circuit conditions. Differential protection relays can be used to detect internal faults within the transformer. Surge arresters should be installed to protect the transformer from voltage surges caused by lightning or switching operations. Transformer grounding is necessary to provide a path for fault currents to flow back to the source. The grounding system should be designed to minimize touch potentials and step potentials, which can pose a hazard to personnel. The grounding conductor should be sized according to the requirements of the National Electrical Code (NEC). Furthermore, transformers play a crucial role in renewable energy systems. They are used in solar power plants to step up the voltage from the solar panels to the grid voltage. They are also used in wind farms to step up the voltage from the wind turbines to the grid voltage. In these applications, transformers help to integrate renewable energy sources into the existing power grid. Understanding transformer nameplates is also vital. The nameplate provides essential information about the transformer's characteristics and ratings. The nameplate typically includes the following information: manufacturer, model number, serial number, voltage rating, primary and secondary, power rating kilovolt amperes, frequency hertz, impedance percentage, winding connection diagram, insulation class, temperature rise, and oil capacity. This information is crucial for selecting, installing, and maintaining the transformer. When troubleshooting transformer problems, it's important to follow a systematic approach. Firstly, check the voltage levels on the primary and secondary sides. Secondly, check the current levels on the primary and secondary sides. Thirdly, check the transformer temperature. Fourthly, check the oil level and condition if applicable. Fifthly, check the bushings and connections. Sixthly, perform insulation resistance tests. Seventhly, perform turns ratio tests. Eighthly, perform excitation current tests. Ninthly, consult the transformer's instruction manual and wiring diagrams. Tenthly, if the problem cannot be resolved, contact a qualified electrician or transformer specialist. Transformer safety is paramount when working with electrical equipment. Always to energize the transformer before performing any maintenance or repairs. Use appropriate personal protective equipment, PPE, such as gloves, safety glasses, and arc flash suits. Follow all safety procedures and guidelines. Never work alone. Ensure that a qualified person is present to provide assistance if needed. Furthermore, understand the hazards associated with transformers such as high voltage, high current, and arc flash. Be aware of the potential for electrical shock and burns. Take precautions to prevent accidents. Always double-check your work. Ensure that all connections are tight and secure. Verify that all safety devices are functioning properly. Before re-energizing the transformer, inspect the area to ensure that it is clear of obstructions and personnel. In addition, transformer efficiency is a key factor in reducing energy consumption and minimizing operating costs. High-efficiency transformers can significantly reduce energy losses, resulting in lower electricity bills. Transformer efficiency is typically expressed as a percentage of the output power divided by the input power. The higher the efficiency, the lower the energy losses. Transformer efficiency is affected by several factors, including core material, winding design, and load level. Transformers with amorphous metal cores typically have higher efficiencies than transformers with silicon steel cores. Transformers with optimized winding designs can also reduce energy losses. Transformers are most efficient when operating near their rated load. In summary, transformers are essential components in electrical power systems, serving to step up or step down voltage levels. Understanding transformer basics, calculations, applications, maintenance, protection, and safety is crucial for anyone working with electrical systems. By following best practices and guidelines, you can ensure the reliable and safe operation of transformers.